Good morning students. Today is lecture 21 under module 7. So, in today's lecture we will discuss the factors affecting the ultrafiltration performance, fouling and how to reduce fouling, and then various ultrafiltration applications. Since there are many ultrafiltration applications and it is extremely wide, so discussing everything is not possible in a lecture like this. So, I have given very few applications in which ultrafiltration plays a very significant role, and we will discuss one by one during our subsequent lecture today. You know, there are different types of factors that affect ultrafiltration performance. The first and foremost important thing is of course your membrane, what is its pore size, then what is the membrane material and its properties. The next thing that comes into picture is the solute, that I am going to separate. So, solute means solute shape, its size, its diameter, okay, and its properties like whether it is charged or what type of charge it is carrying. All these things plays a very important role. Now, apart from the solute and membrane, the other factors that actually play a significant role in ultrafiltration performance, that we are going to discuss. So, the first one is the transmembrane flow. So, you know, the rate of permeation increases with increase in flow velocity of the liquid across the membrane surface. So, this we have discussed earlier also. I will just try to again make you understand. So, let us say this is our feed coming and we are getting here retentate and we get our permeate, the usual cross flow system. Now, what is happening as the progress in separation is happening. So, with respect to times, so a solute started getting deposited on the surface of the membrane. Now, we have discussed in one of our classes that one of the most important method to reduce the concentration polarization, there are many of course, and subsequent fouling is to increase the cross flow velocity. Now, this is what this first line is telling, that the permeation or the transport will increase when you increase the cross flow velocity, because when you increase the cross flow velocity, okay, the higher velocity will try to wash away the solutes that is getting deposited on the surface of the membrane. Now, flow velocity is particularly important for liquids containing emulsions or suspensions. Moreover, higher flow rate means higher energy consumption and larger pumps. This is also not always a win-win situation, that you increase the flow rate, but at the cost of what? Of course, at the cost of energy and pumping costs. So, increasing the flow velocity also reduces the fouling on the membrane surface. Now, please understand that fouling is a consequence of the concentration polarization. So, generally an optimum flow velocity is arrived by a trade off between the pump horsepower and the increase in the permeation rate. You simply cannot go on increasing the cross flow velocity as per our wish, it is not so. So, there should be a trade off. What is the pump horsepower that is actually pumping the feed, and what is the permeation rate that we are getting, and what type of membrane also we are using. So, for laminar flow in thin channel modules, flow velocities of almost 1 to 2 meter per second are used, and in tubular modules, turbulent, where the turbulent flow regimes comes into picture. So, almost we can go up to 5 meter per second. The next parameter is operating pressure. Now, permeation rate is directly proportional to the applied pressure across the membrane surface. Now, this is of course, since ultrafiltration is a pressure driven membrane process, the more you increase the pressure, the more will be the permeation. However, due to the increased fouling and compaction, the operating pressure rarely exceeds 100 psi and are generally around 50 psi. So, in some of the capillary tube filtration modules, the operating pressure are even lower due to the physical strength limitation imposed by the membrane module, because in the capillary system they cannot withstand higher pressure, otherwise they will distort actually. To maximize plant output, ultrafiltration process is usually carried out at a pressure giving a permeation rate close to the limiting flux. Now, it is not desirable to increase pressure beyond limiting flux is reached, okay, as the membrane fouling becomes increasingly important and the flux decline is accelerated. We have discussed what is limiting flux in one of our earlier classes. Now, the next parameter is operating temperature. Now, you know that temperature always necessarily do not play an important role in all sorts of ultrafiltration applications. However, wherever there is a temperature driven separation process, of course, it will play a big role. So, usually it has been seen that the rate of permeation increases with increasing temperature. Now, this is due to the fact that as temperature increases, the retentate velocity decreases, viscosity decreases and the diffusivity of macromolecular increases. Are you understanding? That means, when I am increasing the temperature inside the membrane module, the retentate which is getting retained on the surface of the membrane, of course, in a liquid medium, its viscosity is decreases, because viscosity is a consequence of temperature. So, when the viscosity is decreases, so the diffusivity of the macromolecules inside the membrane, it is increasing. So, increase in temperature up to certain extent, of course, favors favors a high permeation rate. Now, high temperature are not always preferable, as they may even lead to denaturation of certain thermomobile biomolecules such as proteins and enzymes. Whenever I am doing some bioseparation, so I cannot of course increase my temperature. For example, in dairy industries, the normal operating temperature condition ranges from 50 to 55 degrees centigrade, and another important thing is that the membrane which you are using should also be thermally stable. Now, it is important to know that the effect of temperature in the membrane flux in order to distinguish between a drop in permeate due to the drop in temperature and the effect of other parameter. The next is salt concentration. Now, salt is not always used, but certain applications salt is used in a buffer media to enhance the performance. Now, especially for separation of proteins and enzyme mixture by ultrafiltration, the concentration of salt has some effect. In the permeation of enzymes, the aqueous suspensions often contains a combination of salts. So, there may be more than one salt also possible. So, the rate of ultrafiltration decreases with increase in molar concentration. Membrane may not retain the salt, however, because of their ionic nature, some intramolecular association occurs and the rate of ultrafiltration eventually decreases. Now, let us understand and discuss the fouling and flux decline profile in ultrafiltration. Now, you know it is same as in other processes also, but we will quickly go through once again, so that it will also revise your understanding of the flux decline performance as well as fouling. So, one major drawback of ultrafiltration process is membrane fouling caused by increased solute concentration at the membrane surface. So, either it is happening by the macromolecular adsorption to the internal pore structure of the membrane, or aggregation of protein deposit on the surface of the membrane. Now, it is not always protein, it is just for example, I have written its protein, it is any solute that is I want to retain. So, which eventually leads to concentration polarization. Now, the concentration polarization is the major culprit in decreasing the flow rate permeate flux. Usually, two types of fouling takes place, one is adsorption of macromolecules and polymerization of the adsorbed layer. So, due to these two things, fouling actually takes place. You can see the first figure, flux versus pressure. So, you can see this is the straight line, this is the clean water flux or water flux, and this is your limiting flux which we are just discussing. So, you can see this is the standard flux decline mechanism or profile in a ultrafiltration system, and here you can see that when the concentration polarization layer actually is built up, then the flux is declined like this, the red one, and when the membrane starts fouled, okay, then you will get a flux decline profile like something like this. So, this magnitude is been told as been described as the fouling, but it is not measured like that, it is just a schematic understanding. So, the ultrafiltration of feed solution having biological origins are more susceptible to biofouling. Now, in such solutions, there is generally a complex equilibrium setup. Any changes in protein concentration or ionic strength can destroy this equilibrium and causes the protein to be denatured and precipitated. Now, sometimes the protein gets adsorbed on the membrane surface, resulting gradual blockage of the pores. Deposition of proteins gets maximum at isoelectric point. We have understand what is isoelectric point in one of our classes, and when the solute is more likely to aggregate and even greater in the presence of salts, which also augments the aggregation. Now, we are discussing about proteins because proteins are more susceptible to biofouling. Proteins are enzymes, and ultrafiltration has huge application in pharmaceutical or biopharmaceutical or biotechnological industry dealing with various types of proteins and enzymes as well as antibodies. So, the effect of fouling is also severe in the food and pharmaceutical industries. Here the ultrafiltration plants are to be cleaned every 24 hours in order to control fouling. So, frequent cleaning of ultrafiltration systems are required because proteins are more susceptible to fouling. So, let us understand the different stages of fouling. So, usually stages in ultrafiltration fouling is been described by 3 stages, stage 1, stage 2 and stage 3. So, in stage 1 the solvent or water flux decline is happening actually. So, here from here to here. Okay. The membrane may lose 50% of its permeability. So, low concentration of contaminant particles, dust or so are rapidly carried out and obstruct the largest pores. Now, in stage 2 from here to here, okay. So, it is the initial polarization period, that means in which the flux drops due to the boundary layer phenomena. So, if you see again I am trying to draw a membrane. Okay. So, initially the very small particles or this one they will get inside the pores, okay, and they will get deposited also. So, low concentration of contaminants of the particles will this one, most of the times your solvent will pass through. Okay. So, this is stage 1. Then slowly the concentration polarization or boundary layer build up will start. Okay. So, this is the boundary layer build up. So, this is happening due to this stage is happening in stage 2. So, fouling is initiated by plugging of pores with solutes. So, the pores will be plugged with solutes which are either mostly similar in size to it or smaller than it. So, stage 3, this stage, okay, is the period of normal flow operation. So, in which actually the polarized solute molecules may become bound to each other and to the membranes, forming a deposits that no longer responds reversibly to the increasing close flow. That means, what is happening? This is strong interaction between solute as well as solute. So, basically solute interaction as well as solute membrane interaction. Now, this interaction is becoming so rigid that if you increase your close flow velocity very high, okay, then also they are not getting washed. Okay. So, that whatever now you can understand that also some sort of cake or whatever you can call a gel layer formation is happening, and subsequent fouling is getting resulted, and due to that your this one flux decline profile looks like this in stage 3. So, there are several methods to prevent fouling. This includes the pre-treatment of the feed water and cleaning of the membranes. It is very important if you are treating with wastewater, then the wastewater from various streams, whether it is sewage, domestic or industrial, as well as process wastewater from various industries. So, they contains various types of components, suspended solids, dissolved solids, heavy metals, oils, greases, okay, and what not. So, the maximum of these things which are actually TSS, suspended solids and all, needs to be removed before by using a usual filter mesh or screen before it goes to the ultrafiltration system. If we do not remove that, then what will happen is that the plugging of the pores of the ultrafiltration membrane will become very fast, and there will be huge fouling and concentration build up, and your flux decline will be very fast. Almost it will decline something like this, okay, which we do not want. We always want a flux decline profile something like this, right. So, the pre-treatment methods include sand filtering, coagulation followed by an activated adsorption, and dosing by oxidant agents or anti-fouling agent. Different types of pre-treatment methods are there. You can, depending upon what is the wastewater source actually. So, you can either use sand filtering or coagulation to precipitate something, or you can have an activated adsorption system, activated carbon adsorption system, in which most of the pollutants will be adsorbed to the surface of the adsorbents, or you can have some oxidant or anti-fouling agents also. So, the membranes are usually cleaned by chemicals or by backfluxing with pure water and permeate. Once the process is over, so you need to clean the membrane. As we have discussed that if you are treating proteins and all, so every 24 hours there should be a backflushing cycle or cleaning cycle. pH adjustment can be used so that protein solutes will be far from their isoelectric point and so increase their solubility. Our heat pretreatment can be used to accelerate precipitation tendency in fouling substances in certain cases. Example, if cheese whey is kept for 1 hour at 65 degrees centigrade, the immunoglobulins and the fat the two least soluble components of whey are precipitated. And let us see the backflushing. We have never discussed backflushing in detail. Let us just try to understand how backflushing actually happens. So, actually the cleaning process mechanism is that first, once the process is over, so you take out the membrane system, okay, and try to use the fresh water from permeate side of the membrane, and depending upon what type of membrane actually you are having, and then try to clean it. So, once that is over, so at a very high flow rate, of course, which is recommended for that particular membrane module. So, once that is over, then you can, depending upon the nature of the solutes that particular membrane has dealt in. So, you can either use for some detergents or some either dilute little very dilute acid or dilute alkali. So, and then again go for the repetition of the cycles. After successive cycles, when you see the your permeate flux performance is good, or you are getting a good permeate flux, then again you stop this process and again rinse it with fresh water some few times till you get your desired flux, right. Now, let us understand, you see the A figure in which is the normal operation basically. Okay. So, feed is coming here. Okay. So, this is the membrane and you are getting your permeate here and the residue retented here. Now, how do I do backflushing? So, what I am doing is then from the this is a capillary tubes, okay, this capillary systems. So, this particular figures, okay. So, what I am doing is that I am sending the feed here, I will send clean water, okay, maybe deionized water sometimes, but usual tap water also it is fine. So, you send it, then pressurize it, then what you do is that you close the permeate trap or the permeate valve through which the permeate is getting collected. Now, by doing that, what is happening is that we develop certain pressure. The pressure what is developed, it is in between the feed pressure and the permeate pressure. Okay. So, you can see that the when the permeate is not getting actually collected, it is closed, right. So, the permeate as well as the feed, okay, they are exerting some pressure and most of the backwashing is happening in this particular side, in the lower side of the membrane. This is one way. Then what will happen? Then you reverse. Then how what should I do about this area? Now, this is the answer. Then I reverse the flow of the water. So, instead of flowing it from the feed side, I am now flowing it through the retented side. Okay. Then same procedure will happen, okay, and the other half of the membrane will be cleaned by backflushing. So, this is how backflushing is done. This is for example in capillary tube membranes, and usually for any other systems also the procedure is same. So, though we have discussed how to reduce concentration polarization. So, I will just quickly go through, these are some of the other techniques. So, you can use tangential feed flow rather than impact. So, that is direct on flow. So, this method increases the back diffusion of polarized species and reduces the buildup of solute, basically decreased osmotic pressure and gel layer resistance. Another method is introduction of frequent feed flow reversal. Now, this reduces solutes build up at the entrance region by changing the entrance region position. So, just like I was telling now here, if you closely look at this. So, from here, okay, the feed, this is your feed, right. From feed is entering here. So, after successive operations, now you enter your feed from here with the same membrane. So, there is a feed, there is a feed flow port, there is a retented port. Okay. So, you just reverse it after successive direction. The idea is that the entire membrane surface should be utilized for the separation processes, okay, and the concentration polarization build up will also be reversed. So, that the introduction of frequent flip flow reversal, that is called actually. So, then next one is introduction of mixing promoters into the feed channels. Now, this method increase boundary layer mixing, thereby increasing the back diffusion rate, right. Both fixed and moving inserts are used. Then use of frequent pressure pulses of the feed flow. So, this is destabilizes the concentration polarization build up and causes increased back diffusion. So, you are doing the pressure pulsing. So, addition of dynamic particles to feed stream. So, because of the well known tubular pinch effect, added particles will, if chosen correctly, disturb the concentration polarization layer by increasing the back diffusion. So, that means suppose this is the membrane, this concentration polarization is happening, okay, here. you add some particles. Okay. So, what will happen? So, it will try to come here and it will increase the back diffusion. So, when it increases the back diffusion, so the chances of these solutes that is getting deposited on the surface of the membrane here reduces. So, thereby reducing the concentration polarization and of course, subsequent fouling also. Now, let us understand and discuss different types of ultrafiltration processes, applications basically. So, water treatment, treatment of oily wastewater, processing of whey, recovery of coat paint, concentration of latex emulsion, pulp and paper industries application, textile, clarification of fruit juices, PVA recovery in the this one here cloth manufacturing industries and cold sterilization. Now, water treatment is of course an most important application of the membrane processes, membrane technology, whether it is ultrafiltration, reverse osmosis, nanofiltration or ultrafiltration. Now, ultrafiltration is very effective for removing colloids, proteins, bacteria, pyrogens and other organic molecules which are larger than the membrane pore size. It can be used as a pre-treatment to reverse osmosis or for the final filtration of the deionized water. Now, deionized ultrafiltered water is used for many biological applications that are sensitive to high level bacteria, protein, metal ions or dissolved organics. The world's biggest installation using ultrafiltration is reported in the Twin Oaks Valley water treatment plant, that is in San Diego, having a capacity of 100 million gallons per day, Now, the next application is oily wastewater. So, this is one of the most significant application of the ultrafiltration. So, oil in water emulsions are routinely used for cooling and lubricating of tools and dies during cutting, forming and grinding of metals, mostly in refineries, then near metallurgical industries and other process industries of course. The wastewater from these operations contain oil droplets to submicron size. Now, ultrafiltration is used to concentrate the oil water emulsions. Membrane retains the stable emulsified oil, while the water and low concentration of dissolved oil surfactants pass through it. Oil can be concentrated up to about 10% and then it is reused. Now, an oil in water emulsion containing 10 wet percent oil is used as lubricating and cooling fluids for a drawing process involving large metal sheets. So, after drawing process, excess oil emulsion is removed from the cans in a 3-stage 60° centigrade water washing. The rinsing of water of a single production line accumulates about 5 meter cube per day and contains about 0.6 grams per liter of oil. The rinsing water is processed in an ultrafiltration unit equipped with 18 capillary membrane module, providing the area of 18 meter square membrane area. In this process, the oil is concentrated from about 0.6 to 100 grams per liter and without further treatment recycled into the production line. So, the virtually oil free filtered is fed directly back to the washing cycle. So, this water is getting reused basically. So, just closely have a look at this particular figure or schematic diagram which is used to treat the oily wastewater. So, your feed is coming here. So, there is some sort of pre-filtration here, as we have discussed just why pre-filtration is required before it is being fed to the ultrafiltration system. Then it is recirculated here and being fed to the ultrafiltration filter. Here hydrophilic ultrafiltration membranes are being used. Then your permeate is getting collected here and your retented is being recycled to the cleaning tank. Okay. So, in this particular system the choice of membrane also plays a very important role. So, here is you know that hydrophilic membranes are good so that they will not allow the development of your this one concentration polarization. Now, let us understand and discuss the application of ultrafiltration in dairy industries. So, many things that happens in the dairy industry, different processes. So, we will discuss a few. So, the first one is the whey protein concentrate or isolates. Now, ultrafiltration membranes are an essential process technology in the concentration and purification of whey protein concentrate and isolates from cheese whey. Second is milk protein concentrate or isolates. So, the use of ultrafiltration membrane is growing significantly in the concentration and purification of milk protein across the globe. So, the next one is brine clarification. This is also a part of the cheese manufacturing in process. So, the clarification of brine solutions by ultrafiltration is an important step in the curing of cheese by preventing the growth of molds, means fungi growth on the surface and providing an optimal amount of lactic acid for proper curd ripening. Now, let us understand how it happens. Actually, the whey protein concentrate. So, what is whey? The whey is a byproduct of cheese manufacturing and is composed of roughly 0.6% of proteins, 0.2% of non-protein nitrogen, 5% lactose, 1% salt and some lactic acid as well as water at pH between almost 3.5 to 6. Now, it also contains a trace amount of casein fines and butterfat globules and a large population of bacteria. Now, ultrafiltration retains two principal proteins. One is alpha lactalbumin, so which is whose molecular weight is 17,000 Dalton, and another is beta lactoglobulin, its molar mass is 36,000 Dalton. So, these are the two most important or principal proteins along with large casein and butterfat particles as well and the bacteria. Now, ultrafiltration passes water, lactose and non-protein nitrogen through the membrane into the permeate site. So, whey protein concentrate is obtained using ultrafiltration on different whey types, so sweet, acid or casein. There are different types of whey that is coming out of the cheese manufacturing industry process or different types of permeate from microfiltration of milk. Depending on the required protein concentration level, different ultrafiltration techniques can be applied. As for example, dilution with water, also known as diafiltration. So, the final composition of the WPC depends on several factors such as the original composition, the level of concentration, the membrane itself and the processing parameters. That is we have discussed what are the processing parameters today in our beginning of the class. So, the byproduct permeate mainly containing lactose is suitable for further valuable processes such as health supplements, baby food. So, we again go for lactose enrichment. So, this is a WPC system. So, a continuous ultrafiltration system is typically set up stage by stage. So, it is not a single ultrafiltration membrane will do the job. So, they are stage by stage or in series along with diafiltration in later stages to increase the removal efficiency. Okay. So, in between a few ultrafiltration stages which is doing the WPC, there are some diafiltration membranes also installed. So, in the stage by stage configuration, the customer typically increases the spacer size of the element to maximize the solid content during the later stage of filtration. For WPC, microfiltration also a necessary step to lower the fat content. So, initially you use the microfiltration membrane to remove the fat content. Ultrafiltration is then applied to the defatted protein along with the diafiltration for later stage. So, the resulting product is typically higher in whey protein and lower in fat and lactose. So, the next application is milk protein concentrate. So, ultrafiltration is commonly used in the production of milk protein concentrate where it can lead to an increase of the protein content in the total solids. The byproduct, that is the permeate, is perfectly suited for lowering the protein content of the other products such as skim milk powder or many times it is called skimmed milk powder. So, application of milk protein concentrate include dietary supplements, functional food, diet replacements, etc. So, this is flow chart actually. This tells us about how ultrafiltration is being used for preparation of the milk protein concentrate. So, you take here fresh cow milk. So, it goes through the microfiltration as you have discussed. It will remove the fat and as well as other microbes. Then we get a microfiltration permeate. Okay. Then you send it to the pasteurization plant. So, almost 72 to 1 plus degree centigrade for 15-16 seconds. Then you add calcium chelators which is EDTA. pH reduction is also done by permeate additives and acids, ion exchange, and then you pass through ion exchange and cation exchange resins. Then once that is done, you send it to the ultrafiltration which is less than 10 degree centigrade, it is operating. So, then once whatever it is coming from the ultrafiltration system, you pass it to the diafiltration. This is diafiltration at less than 10 degree centigrade with addition of monovalent salt. Then the process is the next process is homogenization, pass through high shear and high pressure ultrasonication, and you sometimes you may need also enzyme treatment. Finally, it goes to the spray drying where the moisture content is reduced to less than 5%. So, basically you make powder, and whatever you may add some MPC 40 or MPC 89, these are stabilizers to improve the solubility, and then you go for packaging and storage. So, this is the flow chart how to prepare the milk protein concentrate. Next one is brine clarification. So, in the production of cheese, salt brining is used to inhibit bacterial growth and to add flavor to the cheese itself. Filtration allows for most of the lactose to be removed for ideal curd ripening, and salting draws moisture from the cheese in order to form the rind and prevent the growth of molds. Growth of molds means the growth of fungi basically. As the need for waste effluent disposal continues to rise, the use of brine clarification through ultrafiltration has become increasingly important to minimize costs and reduce environmental footprints. You can see this is the schematic diagram of the brine clarification process. The ultrafiltration, the brine, the feed brine passing through the ultrafiltration, and the concentrate brine is getting recycled to the feed tank, and the permeate either you can collect it or you can send it to the cheese brine bath here, okay, for the recycle purposes. So, application for ultrafiltration for preparation of lactose free milk. So, in the production of lactose free milk, ultrafiltration plays an important role in achieving a sensory experience similar to that of the fresh milk. Before the milk undergoes an enzymatic process, most of the lactose is removed by means of using ultrafiltration. Now, again remember, in industries a single stage or single step ultrafiltration membrane will never give you the desired result. So, everything is done in stages, or you can call it in series. So, then application of ultrafiltration for decalcification of milk. So, ultrafiltration can be used as a superior separation unit in a decalcification unit for the decalcification of RO, or preferably NF pre-concentrated permeate for lactose production. So, you are removing calcium actually. As calcium phosphate is highly insoluble, so it can be easily removed by means of ultrafiltration following a thermal precipitation process. So, applying this technology will in general result in high quality lactose, where the reduction of calcium phosphate will lead to a higher lactose yield and lower mineral content in the final lactose product, as well as generally improve evaporator running times. So, as you know, in the milk or the dairy industries, so there are so many evaporators which actually is being used to concentrate the milk products. So, if you remove the calcium from the milk, then it will increase the evaporator running times, because there will be no scale formation. Oh. So, depending on the ultrafiltration separation unit's concentration degree, calcium can be refined into a natural calcium phosphate product. So, this is how this is a schematic diagram of how decalcification of milk is achieved. So, skim milk is passed through ultrafiltration to increase its concentration almost to up to 4x at 10 degree centigrade using a 10 kilodalton membrane. Then whatever the retentate is coming, the retentum is actually calcium fortified, it reduced with reduced lactose and skim milk retentate. Then the permeate goes through several treatments. So, you can adjust the pH to 8, or you can go for a heat treatment at 63 degree centigrade for 30 minutes, or a combination of both. Then it goes to another ultrafiltration membrane having 10 kilodalton membrane, and whatever you get the calcium rich retentate, it can be fed back and recycled to the retentate here. Okay. So, you get calcium fortified reduced lactose there, and you get a permeate here. So, student, this is a general schematic of the application of membrane technology in dairy industry. So, it is not dairy industries you just learn now. Today we discussed about MF and UF. how they are being used in dairy industries. So, RO is also being used. So, you can see how it is happening. So, the milk which is coming to the microfiltration system initially. So, it is giving me low fat, low bacteria milk, that means fat and bacteria is removed. So, that can straight away go to the cheese manufacturing, and whatever is coming here is a retented. So, that means the fat. So, that is nothing but your cream. Okay. So, that can be stored or can go to the beverages section. The milk that is coming to the ultrafiltration and it is retented can go to for cheese manufacture, specialty milk product or milk protein isolate. Okay, isolate. So, whatever is permeate, so that goes to again a RONF system to remove lactose. Okay, and whatever will come, that is basically we will have actually lactose free, what you can solvent. Okay. It can be recycled, it is mostly aqueous medium. So, milk that is fed to the RO system. So, in the permeate side we get retented, coming out as a concentrate, can go for a dried milk product, evaporated milk product or specialty milk product. So, this is how the membrane technology, we can see that how the membrane technology plays a significant role in dairy industries. Next application is of course the recovery of electrocoat paint. So, electrocoat is done either by cathodic or anodic electrodeposition. After electrodeposition of the primer coat, the piece is lifted out from the tank and the undeposited loosely adhered paint is washed up with the spray of water. Now, one of the major disadvantages is drag out of the undeposited paints. Now, that is not actually good for the system. So, the ultrafiltration allows the recovery of valuable paint resins and pigments. So, UF allows maintaining the required paint bath control and helps recovering more than 90% of the paint drag out. So, this substantially reduces the load on the wastewater treatment. So, because you have almost removed the paints. So, latex emulsions also can be concentrated using the ultrafiltration system. So, latex emulsions usually consist of 0.05 to 0.3 micron in size of the latex particles stabilized by ionic and non-ionic surfactants. So, some latex stream such as styrene butadiene rubber SBR or PVA polymerization kettle wash are very dilute. So, ultrafiltration is suitable for concentrating this stream from 0.2 to 25%. Then the application in pulp and paper industries. So, some of the applications of ultrafiltration in pulp and paper industries are recovery of lignosulfates from spent sulfate liquors, reduction of color in caustic bleach effluent, concentration of dilute spent sulfate liquor, recovery of lignin from the craft black liquor from the sulfate process, and recovery of paper coating which consists of a mixture of pigment, binders and additives. So, these are used for improving the paper quality. So, membrane of a molecular of cutoff of 3000 to 5000 Dalton are most promising in these applications. So, then textile industries. So, dyes can be recovered by ultrafiltration technologies. The ultrafiltration process can be used with polymeric dyes and indigo, which is in great demand for the manufacturing of denim materials that goes into the blue jeans. So, indigo has a molecular weight of 262 Dalton, but it is insoluble in its oxidized state and can be recovered with using a 50,000 molecular weight cutoff membrane. One of the most important application of membrane technology in an industrial scale is clarification of fruit juices. The meaning of clarification of juice is basically to remove the components which are not required for the fruit juice, as well as these components are actually destabilizes the fruit juice that needs to be recovered. So, the fruits that can be processed by ultrafiltration includes apple, apricot, cranberry, pear, orange, passion fruit and so on. So, after preliminary sorting, washing and peeling steps, the fruits are pressed and centrifuges for the removal of suspended and particulate solids. Now, ultrafiltration process removes suspended solids and turbidity while allowing the passage of juice components and thereby eliminating the need for the aforementioned operations. So, the citrus juices such as orange, lemon and lime are ultrafiltered prior concentration. The removal of bitter components such as limonene, hesperidine, polyphenols and naringin enhances cloud stability and reduces astringency and browning reactions, hence needs to be removed. This is the schematic diagram of the application of membrane technology in fruit juice processing industries. You can see that fruit juice that is passing through the ultrafiltration membrane. Okay, so you get the clarified juice here. Okay. So, that clarified juice is not that immediately collected and packed. So, it passes through separate systems. Okay, here you remove the brine, brine is being added to remove certain other components, then concentrated juice is we are getting here, then it goes to pasteurization and storage. So, whatever the peel and pomace is being retained on the surface of the ultrafiltration membrane, so that it goes through the milling and geometric treatment to remove oil, then it is pressed, okay, passes through a microfiltration membrane, subsequently a nanofiltration membrane. So, whatever you get is the enriched polyphenols, and here you get sugar and mineral. You can understand that the entire fruits whatever is being utilized, various apart from the juice, there are various other value added components that were being also recovered using membrane technology. So, you have removed certain oils, especially oils are prominent in citrus fruits. Then you remove some of the polyphenols which are very costly materials along with some antioxidants. Then some sugar and mineral is also being recovered. Another application is the recovery of polyvinyl acetate PVA. Now, you know PVA is used in processing of synthetic fiber as a sizing agent, okay, in textile manufacturing industries. So, it replaces the conventional sizing agents such as starch and natural gums. So, however, PVA is not biodegradable, hence is more likely to be expensive than other sizing agents. The excess PVA is removed in the desizing bath and then recovered by ultrafiltration. The retentate is reused and permeate water is recycled. So, this scheme you can see. So, this is the complete process. So, in which a 3-stage feed and bleed ultrafiltration system was used to recover PVA in the production of cotton and synthetic fiber. Okay. So, here the ultrafiltration system is being shown here. It is a 3-phase 3-stage feed and bleed system. So, the feed you can see in the feed the PVA percentage is only 1%. So, now in a using a 3 stage 1, stage 2, stage 3 we are enriching up to 8%. So, this is how PVA is being enriched and then recovered. So, the next is cold sterilization. So, ultrafiltration is a means of cold sterilization for many heat sensitive liquids. So, in food processing industries, draft beer provides an interesting example of a product whose feasibility as a commercial beverage has been an outcome of the ultrafiltration technology. So, cold sterilization by ultrafiltration retains the esters on account of which the beer has its draft flavor. Similarly, ultrafiltration plays a key role in pharmaceutical industries for the commercial scale preparation of sterile water and antibiotics. Now, today we have understood the foulings and different parameters that affects the membrane processes, means especially the ultrafiltration, and in a brief we have discussed few ultrafiltration application. As I told in the beginning of the class, there are numerous applications and it is difficult to cover all these things here. So, just try to give a glimpse of the different types of applications. So, most of the materials are taken from this Becker and Kenneth for today's lecture. You can please refer to these 2 books. So, thank you very much. In the next class, we will start module 8, in which we will discuss 2 very important applications of ultrafiltration, which is called a micellar enhanced ultrafiltration. It has been studied thoroughly, and affinity ultrafiltration. Then we will see the ultrafiltration based bioseparation. Thank you very much. If you have any query, please feel free to write to me at kmohanty@iitg.ac.in. Thank you.